turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast, the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. Coming up, scientists get their hands on the oldest ice on Earth, and we've been to see it. But what's it going to reveal? Also, measles is on the up, again, and we find out why. And is humour genetic? We talk to the scientist who studied hundreds of pairs of twins to find out.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Up first this week, a shipment of ancient ice has arrived at the British Antarctic Survey in Cambridge following its extraction from deep underneath East Antarctica. These ice cores are a bit like tree rings. They contain a snapshot of Earth's climatic past, documenting the temperatures and amounts of precipitation. It's hoped that the cores will provide a detailed picture of the last 1.5 million years of climate and atmospheric history, including helping us to understand why the climate goes through warm and cold phases and why the rate at which this has been happening appears to have changed abruptly in the last million years. I went to meet Liz Thomas and the ice at the British Antarctic Survey's Cambridge base.
Right, so we're just going to come on through. We are now standing in our cold laboratory in the British Antarctic Survey.
It is cold.
It is very cold, yes. So we keep this laboratory at about minus 23 to minus 25 degrees.
What's in front of us, Liz?
So what we've got in front of us is a plain-looking white box, but actually it's what's inside that's really important. So what we have here is potentially, or we think, the oldest ever Antarctic ice core.
And you've got some in there. Can we have a look?
Yeah, I will show you. So let me just get this lid off here.
It's like mini drain pipes. It looks like sort of drain pipe sections in plastic bags.
It does. So we have a section of the core that is 3.5 centimetres by 3.5 centimetres, these longitudinal sticks that you can see. And the reason they're in the plastic bag is because we obviously want to avoid any contamination, anything from the atmosphere, from the air, getting onto this ice, because it's incredibly precious.
How did that come out of the ground?
So this is part of a big drilling effort. So in Antarctica, there's been teams of people over a number of different seasons drilling the ice core.
Where in Antarctica is it from?
So this is from East Antarctica, so it's a place called Little Dome Sea.
And the ice I'm looking at, how old is that then? Where's it come from in terms of underground?
So actually these numbers on the bags correspond pretty much to the depth within the ice sheet. So the core that they drilled and they reached the bedrock in January just this year, they got down to 2.8 kilometres, which I think is quite staggering. But the piece of ice that you've just got in front of you, so this is bag 2589, so that's roughly what it corresponds to, so 2,589 metres in the ice sheet.
We know roughly how fast ice builds up. So therefore, how old is that I'm looking at then?
Yes, so we know from how much snowfall we get, and East Antarctica doesn't get very much snowfall. This has actually been built up over a very long time period, and we think this particular piece of ice in front of us could be as old as 1.5 million years.
My goodness. I'm pretty cold in here. You've got a very thick coat and I haven't. Can we get out of here and go to your office and then you can tell me a bit more about it?
Absolutely. Let me put the lid on.
It's a bit warmer in here.
It is a bit warmer, yes.
What will you do with those cores now then?
So the method that we use is something called continuous flow analysis. And we'll take those sticks that you saw, those 3.5 centimetres by 3.5, and we hold them over a hot plate. It's not very hot, about 10 degrees. And that slowly melts it millimetre by millimetre and allows the liquid to then flow into a number of different analytical instruments that look at the different chemistry, the different particulate material. We can look at the composition of the water, and that provides a whole array of information about the climate system and environmental change.
I thought that ice scientists are also interested in trapped bubbles of gas. How would you see those if you just melt them?
So that's absolutely true. So one of the really critical things that we're going to, as a community, look at in this ice core is the new record of carbon dioxide greenhouse gases. We are not going to be measuring that in this laboratory because in order to do that, they have to use a very different method. They have to crush the ice to extract that. But you can see the bubbles. So actually, those pieces of ice you saw, because they've been so compressed, it was very tricky to see the bubbles. It looks very glassy. But under much less compressed ice, you can visibly see bubbles within the ice.
What will you then do with that data? What's this going to unlock that we haven't got access to already?
So currently our longest ice core record goes back 800,000 years, which still is pretty staggering when you consider that humans, Homo sapiens, have only been on this planet for about the last 200 to 300,000 years. But beyond that, we don't have an ice core. And so this is really entering that unknown period of what was the climate doing prior to that.
We do have other measures of the climate, though, don't we? That coral, for instance, captures a cross-section of what the sea chemistry was and that kind of thing. So what can you get from the ice that these other methods that we do have can't tell us?
So there's a number of different archives, and mainly for the southern hemisphere, it's the marine sediment cores, and they're a fantastic record that actually can go back nearly 5 million years. But they do have a few limitations, and that's actually what we refer to as their resolution. There's only a few data points per hundreds of thousands of years. So understanding the different processes that were occurring can be quite a challenge. And the one thing that is unique to an ice core is its ability to capture that record of greenhouse gases. No other paleoclimate archive can achieve that.
What's the big question that you want to get underneath? Now, when you've got this working and with this amazing sort of sample that you've now got, what will you be able to address?
So what we're hoping to address is actually understanding how the climate naturally progresses from cold periods to warm periods. So hopefully people are fairly familiar that we have in the past had what we've referred to maybe as an ice age, these extreme cold conditions. And then today we're in a warm period. Now these cycles are purely natural, so they happen over quite long time periods. And what's interesting is that currently these cycles, or at least for the last 800,000 years, happen on scales of around 100,000 years. So they're fairly frequent, fairly regular, and we think fairly well understood. But prior to this, from the other archives, these marine cores, it suggests that actually these transitions were much quicker. So it only was 40,000 years. And so the warm periods weren't quite as warm and the cold periods weren't quite as cold. So it's a really big fundamental question in the scientific community is how and why did that change?
Any theories?
There's a lot of theories, and one of the things that we're hoping to address is around the role that the Southern Ocean plays in the carbon cycle. So we know our understanding of these glacial and natural variability is that carbon has a very important role in our climate system. And so what we're hoping to achieve is to look at how potentially the Southern Ocean's role in the carbon cycle may have changed over time. So currently it acts as a sink, it draws down CO2 from the atmosphere. But potentially some processes relating to maybe difference in wind strength or the amount of sea ice across the Southern Ocean may have meant that those processes were different in the past. And that's actually a very important question because we think that those processes are actually changing right now and will potentially change more into the future.
It may therefore give us insights into what awaits us as we force the climate more then with man-made greenhouse gas emissions.
Exactly. So one of the key processes is that the climate system is really complex and we need to understand all of these different potential processes and tipping points in the past to help us better predict how it might change in the future. So understanding how the Southern Ocean has acted as a source or a sink for carbon dioxide over long timescales is really essential for the climate models that are tasked with predicting how it may change in the future if we continue to depend on fossil fuels.
And it was pretty awe-inspiring to be looking at that ice that effectively fell as snow 1.5 million years ago. That was Liz Thomas. She's at the British Antarctic Survey and she's got hold of the world's oldest, currently, ice cores that she has just shipped back from Antarctica. UK health officials are urging people to make sure that they're vaccinated against measles following the death of a child from the disease in Liverpool. There's been a huge surge in cases in parts of the UK over the last couple of years, as well as across Europe, and the United States is also experiencing its worst measles outbreak in decades. The cause is almost solely down to under-vaccination. Migration from parts of the world with weaker public health and vaccine programmes, as well as poor uptake in countries, mean that we've fallen below the protective herd immunity threshold that's needed to keep everyone safe. Michael Marks is Professor of Medicine at the London School of Hygiene and Tropical Medicine.
Measles is a viral infection, and historically it was a very common infection of children. And most people who get measles will have an illness where they may have fever, sore eyes, and characteristically a rash over their whole body. And proportion of people that get measles will become more unwell with that. They may get a pneumonia, a chest infection, and some people will have an infection of the brain, but some people can get much more seriously unwell.
We've luckily got a vaccine these days, haven't we? Is that particularly effective or ineffective?
So it's a very good vaccine, probably one of the best vaccines that we have. If you've had all of your doses of measles vaccine, it's probably more than 95% effective at stopping you getting measles. What we know is that measles is very, very infectious. So I'll try and give a comparison to help people understand. If you think about probably the biggest virus we've all talked about in the last 5 or 6 years, which is COVID, on average, one person with COVID will transmit that virus to 2 or 3 other people. Measles, if you had a room full of people, all of whom had not been vaccinated, and there was one case of measles, that person might spread the measles virus to 16 to 20 people. So it is much, much more infectious than all other viruses, and that's why the vaccine is such a critical part.
So if we've got amazing vaccines that are effective in the way you say at combating one of the world's most infectious viruses, why have we got outbreaks?
The first is that because this is probably the most infectious virus we know of, in order to stop spread between people, you need to have a really, really high rate of vaccination in the population, in or around 95% of people. So that's the first thing. You need a really high level of vaccine in the community. And unfortunately, for a number of reasons, rates of vaccination in many parts of the community are much lower than that. They might be 75 or 80%. And although that still sounds very high, because measles is so infectious, you need to get this really, really high level of vaccination to stop transmission.
Many of the victims are really little kids, as in they're under 1 year old, when we get really bad cases and in some cases, unfortunately, deaths. But we don't give the vaccine until more than 1 year of age. So that seems a bit illogical. Why would we wait when the vulnerable period is younger than the age we're vaccinating, if the vaccine is so effective?
If we can vaccinate enough of the population, then we can stop the virus spreading, and that protects those individuals, in this case young children, who haven't yet had a chance to be vaccinated. And that is a concept that has been called herd immunity. So this is the idea that if enough of the population are immune, they cannot catch the virus, they therefore cannot spread the virus to other people, that protects those individuals who, because of their age or because of other medical reasons, can't receive the vaccine. So that's the strategy that we rely on, but it does, as I've said, mean we need to get really, really high vaccination rates in order to protect those individuals who haven't yet had a chance to be vaccinated.
So why don't we just vaccinate them younger?
The baby's immune system is still maturing. You need the right cells to make a good response to that vaccine, because what you don't want to do is give the vaccine and it only protects you for 6 months and you have to vaccinate again and again and again. And what we've been able to establish through studies, if we vaccinate young children at a year and then they receive several other doses in their young childhood, they develop immunity, protection from measles, that lasts for life. So we've got a schedule of giving the vaccines to the children when we know that they will respond well and that they will develop protection for themselves for life.
What's the reason then for the under-vaccination that's going on? It's not just the UK. We've had big outbreaks in the US, in Texas. They've had enormous numbers of cases there. In Europe, many, many countries in Europe that previously had very low levels of measles activity have seen in recent years a big spike again, all attributable to low levels of vaccine uptake. What's behind this?
we have grown up over the last 20 or 30 years when we have had this vaccine. And so most people don't have the experience of seeing this disease and understanding how devastating it can be. So that, I think, is one part. And then the other part are that people have very incorrectly raised a number of concerns over the safety of the vaccine. They have said that the vaccine might cause serious side effects. But really, there is comprehensive data from many, many countries and millions of children who have been vaccinated that show that this is a very, very safe vaccine. So unfortunately, we have this perfect storm: disinformation, incorrect information being shared, telling people that the vaccine is not safe when the vaccine is perfectly safe. And at the same time, people feeling like maybe measles isn't such a big problem. And so we're seeing those two things come together now. And that is meaning that we only have 70 or 80% of the population being vaccinated and many, many children acquiring measles, some becoming sick, and unfortunately, some dying.
Do you think the problem will just take care of itself then? Because so many people will catch it, that one of those reasons you've highlighted, which is that people haven't seen cases, therefore they don't know how dreadful this is, it will educate people and perhaps it will flip the pendulum back the other way? Or do you think we're actually going to have to do something about this?
We will have to do something about it. This sort of disinformation, this misinformation, it's so pervasive now, and we're seeing it spread almost like a virus freely. It's not just measles vaccine. We're seeing declines in the rates of many, many childhood vaccines uptake, as you say, not just in the UK, but across Europe, across North America. And I think we will need public health efforts, both to reassure the population about the safety of the vaccines, and we'll need to think about, campaigns, for example, catch-up campaigns for children that have missed these vaccines. Now you're 3 or you're 4 or you're 5, we need a programme in place to let you catch up and be vaccinated.
Michael Marks at the London School of Hygiene and Tropical Medicine, and we recently actually made a detailed programme all about measles and its biology, with more information on the virus, its origins and how it causes disease. And if you'd like to give that a listen, we've made it very easy to find. You go to nakedscientist.com/measles and you'll find it there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, it's no laughing matter. We want to know, is a sense of humour genetic? Stay tuned to find out. Before that, though, scientists at the Large Hadron Collider in CERN, Switzerland, have been grappling with arguably one of the biggest questions in particle physics, which is when the universe formed and produced both matter and its mirror image antimatter counterpart, where since has all that antimatter gone? If there's only matter left over making up us, then there must have been less antimatter than matter made in the first place, otherwise it would have all cancelled itself out. So how could this happen? Well, there must have been more matter to start with, of course, and scientists have been searching for ways that this could have come about. And this week, they have found one more mechanism which accounts for a few % of the effect. But that does still mean there is a big, exciting gap in our knowledge. And to take a look at the new paper for us, out this week in Nature, here is Professor of Theoretical Physics at the University of Cambridge, Ben Alanak.
We're made of matter and not anything else. And in the theories of particle physics, that's weird. We'd think that the matter and the antimatter, they get produced in equal quantities in the early universe, and they should just annihilate and produce radiation. So really, we should be made out of radiation.
But how do we know that they were made in equal amounts in the early universe? That's an assumption, isn't it?
There's a lot of theory and observation that goes into it. So we know from measuring the afterglow of the Big Bang what was going on. We know there was a hot gaseous plasma, and we know how they behave. So if it's very hot, it's going to be producing matter and antimatter like they do in collisions at CERN, like cosmic rays do. So you can measure these collisions and see, how often matter is produced and antimatter and so on. And you see that it would be with equal rates. You constrain it.
The question then is, well, where's it all gone? Why are we made of matter? Where has that antimatter vanished to?
We know the answer to that. Nearly all of it's turned into photons, actually, particles of light. But the weird thing is, all of the antimatter and the matter almost has cancelled itself out and turned into the afterglow of the Big Bang. All but 1 in 10 billion particles has annihilated into photons. But the one that's left was matter as opposed to antimatter out of that 10 billion on average. So there's some slight mismatch between these in the way these interactions work between matter and antimatter, and that's what's not fully understood in the theory at the moment. There isn't enough of this mismatch predicted by the standard model of particle physics.
Why should there be a mismatch at all, though, Ben? Why shouldn't we make equal amounts of matter and antimatter, and as you say, then all just turn into radiation? Why is there a disparity in the first place?
We don't know the answer to that, really. I mean, the theory can describe it if you have 3 families of matter particles, which we do, and they have complex masses. So, they involve these imaginary numbers, the square root of -1. So you describe it in this way, then you can get a little mismatch in some of the interactions. It's actually weak nuclear interactions that have this mismatch. In these interactions, you can favour one over the other a bit, but actually, with the measurements that we've done with these weak interactions, there's not enough. And in fact, we should have nearly cancelled it all out. So this is pointing to new physics. There must be something new, something wrong with the theory, something missing that provides this mismatch.
And how are the scientists at CERN trying to probe that?
They produce particles which then decay in 2 different ways into the matter particles and some antimatter particles, and the exact opposite. So actually, this recent measurement is lambda B baryons, they're called, decay into a proton, a certain kaon, a couple of pions, all right? But you compare that with the rate that they decay into an antiproton, the anti-kaon, and a couple of pions, and see if there's any difference. And so if you see a difference, you're measuring this mismatch in the actual interactions of the particles themselves. And so you can try and help to constrain what's going on.
Do they see an asymmetry then? When they do this, do they see an asymmetry? And do they see an asymmetry which is a closer fit with what we observe when we look at the universe and relate that to the theories that account for why we're here?
With the recent measurement, they see a few % asymmetry, and that isn't enough information to tell, actually, whether there's enough difference between matter and antimatter. They've also measured it previously in other types of particle, and with the current theory, it's nowhere near enough. It doesn't give you enough difference between matter and antimatter to explain why we're made of matter and not photons.
Is it fair to say then that they can add a few % on to getting us closer to explaining the asymmetry that we observe, but there's still a gap then? There's still something that we can't explain?
So the few % is the experimental measurement in the decay, but actually it's orders of magnitude with the amount of matter that's around in the universe. So really, there's got to be some new physics. There's got to be some new forces and other particles which explain why there's such a big disparity, because it's just not described mathematically within the theory that we currently have.
What do people think might be going on? I mean, there must be some ideas that we can then test.
There are many ideas. There are proposals for heavier particles which decay and which differ a lot. So new heavier particles which are not in the standard model.
I was sort of surprised when you just said that, because I thought the whole point of the standard model was it's now complete. We understand it all. We have things like the Higgs boson in there. We have the picture. So you're saying the standard model isn't complete. It's potentially wrong.
Absolutely. In fact, it looks, for example, because of this problem, that it's wrong. And so that's why physicists like me are still very interested in looking for new particles and forces. So the classic way that you would explain this is with something called leptogenesis, where you invoke some heavy right-handed neutrinos, and they might decay in very asymmetric ways to matter and antimatter. And in fact, there are other reasons to suppose that they exist. The strict standard model says the neutrinos shouldn't have mass, therefore they shouldn't be able to oscillate into each other. So there are other measurements which indicate, that the standard model is incomplete.
Is it within scope of what we've got at the LHC and so on to try and probe this, or do we need a bigger boat, as they say in Jaws?
If you're lucky, the LHC can probe it and discover whatever it is. But there are many proposals which you wouldn't be able to do with the LHC because it's not powerful enough. And in particular, this leptogenesis idea, that's unlikely to be able to be probed by the LHC because the particles involved would be predicted to be just too heavy. There are proposals to build yet more energetic colliders. That's one way. Cosmic rays actually are an interesting source because they come in with very high energies. I mean, you get collisions at energies of a million times higher than the Large Hadron Collider. But that might be one way, for example.
So nature may have provided us with the space equivalent of the LHC to see sufficiently powerful particle collisions that can answer those sorts of questions. How intriguing is that? Cambridge University's Ben Alanak there. The comedian Tommy Cooper's legendary catchphrase, "just like that," encapsulates his effortless comic timing. But was this comedian's sense of humour written into his DNA? A study conducted in Cooper's native Wales, involving over 1,000 twins, has cast doubt on any strong genetic link to comic talent, though. Instead, the evidence suggests that whether someone is funny or not is probably shaped more by their environment and life experiences. Here is Gil Gringros at Aberystwyth University to tell us more about it.
There's a lot of research about the genetic basis of many cognitive abilities, such as creativity and intelligence. And basically, most psychological traits has at least a partial genetic basis. So my prediction would be that humor as well will have a genetic basis.
Tell us about the study then, how you designed this in order to try and test that whether there is a genetic element to it.
We use a twin paradigm, which means that we compare identical twins to non-identical twins. The method allows us to separate environmental and genetic factor because the assumption is that twins, no matter if they're identical or not, are raised roughly similar by the parents. So any differences that we find will be due to their genes. Now, if identical twins are more similar on a specific trait like humor than non-identical twins, we can infer from that the trait has a strong genetic basis.
Because, of course, one of the hardest things in this sort of situation to disentangle is the influence of the environment, isn't it? Because when you grow up together, you're in very similar sorts of environments. You've got the same parental influences, the same educational influences, that kind of thing. But how do you judge what's funny? Because some people find some things very funny and other people just leaves them cold. So how did you judge that's a funny person and that's not a very funny person in order to then make a valid comparison?
Humor is, to some extent, subjective. However, we found in different studies that people tend to agree to a large extent on what's funny or on what's not. What we did in our study, we gave people cartoons without a caption and asked them to write a funny caption to the cartoon. Then later, we gave these captions with the cartoon to judges that didn't know anything about the study, that didn't know the age, that didn't know the twin involved, the gender, and so on, and just asked them to rate it from 1 to 5. And each caption was rated by at least 5 different judges, and they were mostly in agreement with that. And that's how we knew who were the funnier individual and who were not.
Was there a genetic slant in this? Do the identical ones show that their ability to be funny is strongly genetic or not?
So surprisingly not. So this is kind of counter to all the research really in the field. We found that there is no genetic basis for humor ability. Now, this is, of course, the first study that actually examines this question. So I'll be cautious about the conclusion. But what we found is that the sources of individual differences were solely due to environmental factors, both the shared environment, like the parent, and then the non-shared environment, the unique like friend that each twin has.
How did this make you feel then? Because obviously you went into this thinking, we're going to see a strong genetic effect because the brains are going to be wired in a similar way in these identical twins, and that's going to make them think along similar lines, and I'm going to see a strong genetic correspondence to the humour that they are able to express. You didn't find that. So did that make you laugh?
Yeah, funny in a more disappointing way, in a sense. Yes, at first I was a little disappointed, but then again, science is unpredictable. So sometimes you don't get the results that you think they are. Otherwise, it won't be very interesting. And maybe we found something new. Maybe humor as a trait is very different than intelligence and creativity because it involves a lot of different aspects, facets. It's not like a single thing to measure. And also, our task was slightly artificial. Writing captions is not something that people use every day. So maybe we need to look at how people use humor in their daily life and how they interact with others and how humor like erupts spontaneously in conversation. That will be maybe a more adequate way to measure the genetic factors of humor.
And where next then? Now you've killed that hypothesis. What next?
Well, the next step is actually to try to replicate the study, and we're currently running a replication study with a different set of twins. And one of the problems with our study was that our sample was quite old, about 66 years old, also skewed mostly women. So that might have an effect. So we have a different kind of a cohort group in a different culture in Finland, and we'll see if we get the same result. If we do, then we'll have more confidence that indeed humor doesn't have a genetic basis.
And a famous comedian once said, there are 2 rules to successful comedy. Number 1, always leave the audience wanting more. Ba-boom. Gil Greengross, he's at Aberystwyth University, and that study has just been published in Twin Research and Human Genetics. Well, now it's time to go nuclear. James Titko has the latest question of the week for us.
Hello, naked scientists and James. It's Laurie in France here, and I've got a little question about electricity, really. If we can put small nuclear reactors on submarines and Mars rovers, why can't those small nuclear reactors be used along with sustainables to power our towns and cities? Thank you.
Thanks, Laurie. Nuclear reactors split the nuclei of heavier atoms from the periodic table, most commonly uranium, in what's known as a fission reaction. The energy released from this process can be used to generate electricity for national grids. Unlike coal, oil, or gas stations, nuclear power plants do not produce CO2 during their operation, and they're expected to play an increasingly vital role in the clean energy transition. You're right that nuclear reactions are also being harnessed to generate the energy needed on board long missions to the depths of the ocean and the surface of Mars. So, is nuclear power the fix-all to every energy challenge? Here's Simon Taylor, Research Associate at the Energy Policy Group at the University of Cambridge.
It's possible to create a workable nuclear reaction that allows you to generate electricity on a variety of scales, including very small. The idea of putting them on a Mars rover, or indeed on submarines and some ships, is because they can provide energy over a very long period of time in a very reliable way, in a way that you couldn't achieve with fossil fuels. If you're thinking about a Mars rover or even on a nuclear submarine, cost is not the main consideration. But if we're thinking about providing electricity for homes and businesses, cost is pretty important.
Mars rovers use something called radioisotope power. Radioactive plutonium gives off heat as it decays, designed to produce 110 watts of power, about the same used by a light bulb. This powers the rover's instruments and keeps it warm during the freezing nights and winters on Mars, and as the isotope of plutonium being used has a half-life of 88 years, it will provide energy for as long as the mission needs. But meanwhile, if we're talking about nuclear reactors to power our towns and cities, that's very different. We need them to be affordable, to work at scale, and produce much more energy. But recently, there has been interest in using smaller reactors to be able to do this.
The history of not just nuclear power stations, but also coal and gas, is that bigger has generally been better. There are quite good reasons for believing that there are economies of scale. There are really 2 parts to this. First, there are a lot of fixed costs to doing any project to build a new power station, things like siting and permissions and so on. Those are the same pretty much whether you're asking for a 10 megawatt power station or 1,000 megawatts. Secondly, a lot of the equipment that goes into nuclear power stations is the same as for other power stations, other thermal power stations. And generally speaking, it doesn't cost 3 times as much to build a reactor 3 times as big. What's new now is the idea of small modular reactors. Big nuclear reactors, at least in Europe and the US, have proven in recent years to be extremely expensive to build. It's the construction cost that's been the problem. And small modular reactors hope to be able to overcome this by being made from more modular components. That's to say, essentially a smaller number of relatively standardized components, which can be produced at cheaper cost because you're mass producing them, maybe not mass producing in the sense of a car, but producing far more units, and also which allow you to benefit from the quality control that you get in a factory as opposed to building out on location.
So, Laurie, while the technology on board Mars rovers and nuclear submarines are very cool applications of nuclear physics, this model isn't right for powering our towns and cities when it comes to the economics. But smaller nuclear reactors are being explored, and at least in principle, small modular reactors may allow us to have affordable, cheaper nuclear power for the grid than traditional nuclear power stations. There are a number of small reactors in operation, but to test the theory properly on their claimed economies of scale, we need to see a few more be constructed and the effects of that mass production. Thanks so much for your question, and to Simon Taylor from the University of Cambridge for help with the answer. Next time, we're answering this question.
I'm Jeff Frid in Toronto, Canada. My question is this: are there any ways now, or anticipated, in which AI will cause or encourage actual reductions in greenhouse gas emissions and or lessening of environmental degradation? Or is AI all negative on the environmental front? Thank you.
And if you reckon you know the answer, or you would like to share a question of your own for us to delve into on your behalf, why not write in? It's chris@thenakedscientist.com, or you can go on our forum. That's at thenakedscientist.com/forum. There is a dedicated question of the week, QOTW board there, where everyone is debating both this and past questions of the week. Some great reading fodder over there, nakedscientist.com/forum. And of course, again, drop us a line if you have a question or a solution to a question of the week. chris@thenakedscientist.com. Now, just before we go, a lot of you have been getting in touch with expressions of support and also very generous donations. Thank you so much to everybody who's got behind us. It's been incredibly touching and humbling. We've read every single one of the letters that you've sent in, and I have tried to reply to as many people as possible. And also thank you for the donations that have come in. If you haven't heard from me yet, I'm really sorry. The volume of what came in meant that there just weren't enough hours in the day yet. It doesn't mean that I'm not very grateful, and I haven't read every single one of your communications. So thank you very, very much indeed. By way of an update, we thought we'd do something a bit special, because I do now have some information which I'm going to share with you. We'd like to do this next week, on Wednesday, on the 23rd of July, by launching something new, which we're going to call Naked Night. It dawned on me when I was reading your messages and your communications that there's a huge community all over the world of very special people out there, and the vast majority of us have never met each other. And it might be very nice to actually get together, perhaps once a month, so we can do something a bit different and a bit special, but it gives people the chance to actually see one another and interact with one another rather than just being consumers of this programme. So I'll be giving more information next week as more programmes come out with how you can join us for that live event on Wednesday, the 23rd of July. The link will be nakedscientist.com/naked night, nakedscientist.com/naked night, but I'll put reminders and more details into the next programmes that we publish to remind you to come and join me on Wednesday. It'll be Wednesday evening UK time. More details next week. And it would be lovely to see as many of you as possible. This would just be to bring you up to speed, give you a bit of an insight, and tell you what we're going to do next and how Naked Night is going to take shape in the weeks to months ahead. So I hope as many of you as possible will come and join in and hear what we've got planned. In the meantime, thank you very much again for listening to us. Do join us on Tuesday when we're going to meet the data scientists who are hoping to improve the quality of life in care homes. And thank you to Rolls-Royce, who support the Naked Scientists, and we're very grateful to them as well. Thank you very much to the team who work so hard on this programme, and to you for supporting us and listening to us. Until next time, goodbye.